Good afternoon, everyone. Thank you for joining us. So today we're going to be talking about electrical safety standards related to NFPA 70E and how that intermingles with the OSHA standards. Oddly enough, there's not a lot of OSHA information related to arc flash stuff other than the utility standard that was updated in 2014. However, there is language in 1910-335 that requires employers to provide protection for the parts of the body that are affected by electrical hazards in the workplace. And so it's very vague. It was written in 1984, or at least promulgated in 1984. And it's but it still works today because it is so general. So that's a section that they would use to say that you are required to do this safe work practices and assess to determine what that is. And then of course you could use NFPA 70 as a guideline. So that's how they kind of intermingle together. So what are we going to talk about? We're going to define what an arc flash accident or incident is and how that all works. So this is directly related to arc flash. We don't get much into the shock issues. We still have more fatalities, actually most fatalities in the shock area. Arc flash are related to more serious incidences that are burns and debilitating burns, but they don't typically result in fatalities as much as shock would result in. So both of these need to be trained for qualified employees. They all need to have this training. But this arc flash is what we're focusing on today, for at least a short duration today. We'll talk about why they occur. We'll talk about different scenarios. We'll get into the OSHA requirements. We'll talk about understanding advantages of an engineering study versus using the tables in NFPA 70E. Although that's a good backup, it's not always accurate. We'll recognize methods for mitigating the high arc flash hazards, and then we'll talk about some liabilities and so forth. And that's sort of our game plan for today. And by the way, let me go back one. This was me in a picture back in 1992. So I've been around doing electrical work since 1978, and I've had a whole bunch of different kinds of jobs over the 20 years that I worked in the field. And then since that time, I've been more doing consulting type of work and safety regulation type work. All right, so what are the standards that we're dealing with? So first off, there's the OSHA 1910 standard where you can have subpart S and 1910-269. In the construction area, you have 1926 regulations, and you have subpart K and subpart V. So OSHA 1910, subpart S, and 269, subpart V, and subpart K, and 1926. NFPA 70 has been around since 1976. That was actually born when OSHA requested NFPA come up with some information so they could create a standard in electrical safety. And from that 1976 pamphlet, it was pretty small at that time, subpart S was born, and subpart K in construction. The National Electric Safety Code came out with arc flash information, mainly for utilities like work, more medium voltage type stuff, although it had 480 volts and all that kind of stuff in there as well, but it kind of pertains more to the utility standard because of the reference in 1910-269, the utility standard to this standard. So that came out in 2009 with some arc flash data, and that's what we had at the time. And then there's IEEE 1584, which came out in 2002 originally. The most recent one is 2018, came out last year updated for the arc flash guidelines for arc flash analysis. So what is an arc flash? So an arc flash event is incident energy that's caused by a short circuit or a ground fault, and we'll talk about what that is in a minute. So it reaches the surface of the sun, the temperature of the sun. It's an immense amount of heat. It goes very fast. It's a big bang, and it's all over. So this is an instantaneous moment in time that you see. And in that instantaneous moment, the consequences are whatever they are. You can't take it back. You've got to think about what the risks are and the hazards are and protect yourself for the worst case before these things happen, so that at least when it does happen, it will damage the equipment, but you'll go home in one piece because of the protective equipment that you have on. So let's see if I can advance this. So the next thing, the box effect. So in the panels, it becomes almost like a cannon effect because it's directional. It has one place to go, and that's outward once you have a door open. So it's about 10 times greater in a box than it would be up in open air. So you don't see linemen, for example, with suits on because of that. The capacity of this arc flash incident energy is basically based on the energy that can cause a thermal burn greater than 1.2 calories at 18 inches. So the 18 inches is irrelevant kind of, because 1.2 calories is the point at which your skin will receive a second-degree burn. So calories is the measure of energy, the sensitive energy. It has the pressure and all that with it, and also the heat level. And so if it's greater than 1.2 calories per square centimeter as exposure, then it will actually cause a second-degree burn, or could cause a second-degree burn where your skin bubbles up. Below 1.2 calories, it would be like a first-degree burn where your skin's like a sunburn. So that's kind of an important number to remember, 1.2 calories per square centimeter. The copper vapors expand 67,000 times. You have hot air expansion and molten metal and shrapnel. And that's something to consider too, because you may determine what your risk is at 1.2 calories, how far out that will go. But beyond that, you're still going to have molten metal flying out. You've got a lot of expansion going on. So that's something to think about as well. You have pressure waves and sound waves. Your pressure waves are 2,100 pounds per square inch. Your sound waves are 140 decibels. So it's a very loud noise. In 1992, I was closing a switch in the Burlington airport, and it blew because of a dead short on the load side. And when it did, it was such a loud bang that I couldn't hear for 3 hours. And that night, I had ringing in my ears. And unfortunately, it never went away. So I have tinnitus from that one event, 1992. That was a long time ago. So hearing protection is required for doing electrical work as well. You have intense light, so you have to have shields that are tinted because of the intense light. So that's kind of the art class overall. So what do we have to know? First off, we have to know what is the calorie rating at our working distance. And typically for low voltages, under 600 volt stuff, that's at 18 inches. That's how far we would work away from it. So we have to determine what that is. That would be the life-threatening kind of level. So closer in, like where your hands might be, is going to have a higher arc flash, and you could have burns to your hands. But so we don't have to necessarily determine what that is. The good thing is arc flash rubber gloves with leather protectors provide arc flash protection now as well, so that's a good thing. So that's one thing we have to know is what is at our working distance. The next thing we have to know is what is the arc flash boundary? How far out does this arc flash go before it drops to 1.2 calories? On the right side of that yellow line might be over 1.2, where we could have a second-degree burn. So therefore, we need to have arc-rated clothing, and we need to have a shield on, and some other arc flash protection on our hands and leather boots and so forth within the boundary. On the outside of the boundary, you could have cotton clothing, natural fiber clothes, that kind of thing, and not have to wear a shield because you only maybe have a first-degree burn if it were to happen. So that's an important boundary to know, and that's on the engineering labels that would be done to tell you what that is. So what causes it? First off, there's a ground fault that could go from a grounded point, so there's part of the case that would go to a part of the phase. That's one of the phases of this three-phase system. So if you have a short circuit would be from phase to phase, and that would cause an arc flash event that would be greater than a ground fault. Thing is, with 480 volt systems, the air can become ionized, and it could turn a single-phase fault into a three-phase fault very easily, whereas on 208 and 240, it typically won't travel from phase to phase unless you have a high level of available fault current. This is just on the lower bottom, there's a little calculation on how to determine what fault current is. I put that in there, but it's just to give you an idea. On a 500 kVA transformer, you have 600 amps of continuous load capabilities, but your fault current could be 120,000 on that same transformer. So it depends on a few different things, but that's one of the things that are part of how big of an arc flash this actually can be. One is what is the available fault current, and the other is clearing time. So a breaker or a fuse trips in a certain amount of time with a certain amount of current, and the faster it operates and clears the fault, the smaller the arc flash is going to be. So the arc flash level is directly proportional to clearing time. So if a fuse operates and opens up in a quarter of a cycle, it's going to be very, very fast, and it's going to have a small arc flash. If it's a VFD, a variable speed drive with 20 cycles of clearing time, it could be a very large arc flash because it's going to be directly proportional to that time. The more time it feeds the arc flash, the bigger the arc flash gets. So that's part of our risk assessment as qualified people, to know what are we working downstream from to make sure that that we know what that arc flash level is. Okay, so this is just a little arc flash assessment, an actual assessment to give you an idea. So we had done this one about a year ago, and this company had changed their switchgear and they put in a smaller rated. So this is a 1500 amp switchgear, and it was replacing a 3000 amp switchgear that was installed in the late 50s. So there was an older transformer outside that was a 4000 kVA transformer. So it's a large transformer with a low impedance rating. So the arc flash boundary was 215 inches, and the calorie rating was 96 calories per square centimeter. So that was a very high, extremely high level arc flash. So the arc flash level is going to be huge on that, mainly because the transformer is an older transformer with a high impedance, and it's very big. So there's a lot of available voltage fault current from that. Downstream from the main, the arc flash will go down, but because you have this large arc flash in the same switchgear, you have to go by that one label. The switchgear only will have one label. What's the worst case? And so that's going to be a high level, and this is not going to be enough. So you're not going to be able to do any work on there without shutting it down. Now, what they ended up doing eventually is getting a new transformer installed by the utility and brought it way down from 96 calories down to 28. So, I mean, they ended up putting a 1500 kVA transformer with a 5.9% impedance, and it really made a big difference in the arc flash level. So there's ways of mitigating it for sure. Now, coming off the main distribution panel where that smaller arc flash is, that's the feed that's going to go to this bus duct. And the bus duct is now down to 55 inches for an arc flash boundary. It's at 18.6 calories. So to go up to that bus duct and change out a fuse, then you're going to need to have a suit on, and that's going to give you the level that you need. So you could use a category 3 suit, but most companies and the people just have one level, which is the 40 calorie suit. From there, it goes down to a panel, and the panel now is dropped down to 33 inches for the arc flash boundary, down to 7.6 calories per square centimeter. And so that means you're going to be over 4, and that's going to require a balaclava hood, a shield, and a coveralls or clothing that is greater than 7.6. And then from there, you're going to go downstream, probably from one of the other breakers, and you're going to feed this disconnect switch. You're down to 1.8 calories. So you're still over 1.2, which means you're still going to wear a shield for this event, for this protection. And then from here, the fuse feeds a control panel, and the control panel's got a low level. It's down to 0.5 calories, so it is under 1.2. So you're still going to wear a shock protection, and you might have an arc flash protection, an arc flash issue at his fingertips. But at 18 inches, he doesn't. So he doesn't need to have a shield, doesn't need to have arc-rated clothing, and he just wants to make sure he's got cotton cap on and a cotton. That you don't have to have a cotton cap. You just have to have if you're going to wear a cap, it needs to be cotton, not polyester. Because you don't want any meltable fibers around anything to do with any arc flash, because it will melt and it will get right into your skin and have to be surgically removed in some cases. So it's pretty bad. So this gives you an idea how it starts off the main switch very high, steps down at the bus duct, steps down at the panel, steps down at the fuse. Generally, you're going to, once you go 3 levels down from the main switch, you're at quite low levels most of the time. Not always, but most of the time. This is kind of showing a little bit higher levels that you would than you would normally see, because I do wanted to show the different levels of protective clothing. Okay. The next one we're going to talk about is we're going to get into the various arc flash causes. So motor control centers are the #1 area for arc flash incidences. They're not always the most serious, but they were the most common, and they happen often when you're replacing a bucket. So that's racking out a bucket or something like that. So that's something that happens quite often. Let me turn this for a second. Okay, this is dust levels, conductive dust. That's also an issue. So it's something to think about. If you have combustible dust or dust issues in the plants you're working with, you want to make sure that you mitigate those issues as much as you possibly can to prevent these things from happening. And usually there's a high level of maintenance, and you also have to go with class 2 hazardous equipment, class 2, class 3. Another thing that causes flashes is wiring system, wiring protection. So we have on the left-hand side, you see the arrow that's pointing to a bushing or a connector that doesn't have a bushing on it. One to the right of the arrow has the plastic bushing on it. So that has to be screwed on before you run your wire, and that wasn't in place. So that you can see the wire is starting to get skinned. On the one at the bottom, you can see there's a wire that's going through a hole. Of course, all these holes, each one of those is a violation of OSHA to have open holes like that. but also you can't run flexible wire for permanent wiring, and you can't run it in a hole without a connector. So there's actually going to probably be about 4 different OSHA violations on this one picture. And on the right, you can see the same kind of thing. You got the metal that's been, it probably had a protector at some point to protect the wiring, but long gone, and that's going to be a problem, and it's going to wear those wires out for sure. So that's one problem. Then we have improper maintenance. So there's a couple of incidences here. So the one on the left shows switchgear that there was an operation. Once it was operated, there was actually a failure inside the switchgear, and it blew the door completely off. You can see the 2 doors to the left. They're actually quite heavy doors, but it blew it right off completely. The person that was doing the switching was blown about 25 feet back and ended up in the hospital for a while, but ended up okay. So that was lack of maintenance on that one. The one in the middle and the one on the right, they're the same one, just different views. This is a grounding switch. So this grounding switch was closed in on a live bus. So there's supposed to be an interlock system, and there is an interlock system, but it was not functioning. They closed this wrong switch in. They should have been closing it on the one next to it that had been open, but they went to lunch, came back, closed it in on the wrong one. The interlock failed, and it allowed them to do it. So the only good thing is it was way up high so that nobody got hurt. It could have been more catastrophic than what happened. So you got to be careful on maintenance. If you know things that are happening out there, you have to fix them. Connections not torqued properly. So in the middle, you see the infrared test. That's something that is great to do. You're picking up things before they happen. I strongly recommend all companies do infrared testing once a year. And so they picked up this hotspot, and the hotspot, come to find out, was because the connections were over torqued. And that happens a lot. So these torque wrenches and torque screwdrivers should be part of everybody's toolbox. So every connector, if you look at the picture on the right, there's a little screw in one of the connectors there. That has a torque setting. That would be in inch pounds, but then you may have a bus bolt that would be in foot pounds. That would use a wrench. I don't think you need to have an insulated tool because I don't personally, I would not torque anything in a live state. I would only do that in a de-energized state, and therefore I don't really need, I have torque wrench and torque screwdrivers, and they're not insulated, and I never had to do anything with them in a live state. So, and I would never do that. So I would guess, and I've been an electrician for many years and never had to use an insulated tool for that. So, but torquing all connections and all connectors should be torqued. I mean, and most of the time people do over torque, and that's the problem. On the left picture, you have some plumbing clamps. Those are not splice clamps for electrical. So everything that you use for electrical and most other things, they need to be labeled and listed for the job. So you need to have a splice kit or splicing information or test kit that is labeled and listed by a nationally recognized testing lab in the country and listed as OSHA nationally recognized testing lab. And then you have to use it according to the specifications from the manufacturer or the standards. In the middle, there were some wires to the right and behind the mechanism from that switch handle. That mechanism rubbed on those wires and caused this door to be blown open when it breached the insulation. So the problem with that is these wires, this is not a raceway on that side. So the wires should have been run on the other side of the box. Some of these boxes will have a cover that you can use it for a raceway on both sides, but this one did not. So you've got to go by the manufacturer requirements for installation, and it was not done that way. On the right, this is just bad practice, it's having storage. This was a distillery, and you can probably tell that, but it's not a good place to store stuff. You don't store things in an electrical panel, and that's just asking for accidents. Improper use of tools. So tools can cause a short circuit, especially non-insulated tools, but you shouldn't be going into energized stuff anyways if you can help it. This was a situation where they're removing a bucket. The picture on the left is a motor control center bucket. They have to take the screw out where you see the screwdriver tip, and then where you go a few inches away, that's where it made contact with one of the phases. And then it ionized the air and it traveled. This plasma caused a short circuit to go from phase to phase. So the single phase fault in 480 turns into a 3-phase fault very often if it lasts enough time, a few cycles. So that's what happened, and it ended up being some significant burns as a result of this. Now, an insulated tool, this would not have happened if you had an insulated screwdriver. Not that you would want to do this in a live state anyways, but that would have prevented it from happening. Same thing down below, to the right rather. So the fuse on the floor was being replaced. That was the new one. So they pulled out the old one using the channel locks, and it caused a short circuit. And this person was wearing polyester, which melted, and they had it surgically removed and had significant damage to his body. So that could have been avoided partly if you had an insulated fuse puller. And so if you're, and also if you de-energized the whole system, that would have been avoided as well, of course, which is something that OSHA would require for lockout tagout. This is using a tool that actually was cutting into a live wire, and now this live wire's got a shield on it that's grounded. So as you go through the shield and the phase, it short circuits the ground, and then there's a significant arc flash. You can see the clothing that was arc-rated clothing and the yellow hard hat that was being worn by that individual. Over duty. This is something that a lot of companies don't realize. So 1910, 303, B4, and B5, those are the sections of OSHA and Subpart S that say that you shall do a coordination and a short circuit study. They don't say it quite that way, but that's exactly what it is. So a short circuit study is you have to know what your fault current is so you can have equipment that is rated for that fault current. Companies will go and replace a breaker. They'll go to Home Depot or Lowe's and pick up a breaker. It fits, it works, but it's only rated for 10,000 amps. That's the highest rating you're going to get for a short circuit rating on the electrical panels and breakers. And it's because they're made for home, and that's the only arc flash, the fault current that you have is adequate for that. But a lot of these places, you can be up to 200,000 amps of fault current at these places, and this is what happens to them. And of course, they don't operate within the time current curve of the breaker, which is also showing in the picture above. Now, you see the picture with the various colors of lines. Those are each color is a time current curve for a different breaker, and they should all be staggered, one after another, not on top of each other like you're seeing there. Because what will happen if you do it like this is that it won't, like if you're in a bathroom and have a failure on a blow dryer, you want the breaker feeding the bathroom to trip. But in this case, it's kind of overlapping. So you may have the main breaker to the panel trip instead of that because it'll be faster. And so then you now have a total outage of the whole floor that it's on instead of just the bathroom. So that's coordination. So that's the other part, B5, that in OSHA, that you do a coordination study to make sure you know what it is and make sure your breakers are not over-dutied. The arc flash level is going to be much greater on the one in the middle. That's a 600 amp breaker. And if it's over-dutied, it may not operate in that time current curve, and it's going to cause a lot more arc flash hazard. And that's the problem with that. But here's racking in a breaker in the wrong position. It should not be able to do that, but if the maintenance has not been done properly, it could be done. It's a possibility. So the controls are not functioning properly or something else is happening because you didn't do what you should have done. And part of that is not knowing. But you can see the suit here, and then this employee was in the hospital for a week. So they survived it. The suit did its job, but this was 104 calories or 110 calories with a 40-calorie suit. So it did its job for sure. This was installing a watt-hour meter, kilowatt-hour meter. So 480 volts. He did not have a shield and a balaclava hood on like he should have had, and that would have avoided a whole lot of injuries. So he had gloves and leather protectors and arc-rated clothing, so that's all good, and that gave him the protection that he needed to see under his neck. Where the arc-rated clothing was, it gave him full protection. Notice the glove on the left-hand side of the picture. That's got a burn on the finger. That is from a ring, and that's because of ionization of the air. It's like throwing metal in a microwave oven. There was no hole in that glove. There was no breach in that glove that would have caused a shock or anything like that. That ring heated up from the inside out, and that's from the air becoming ionized, and his finger was significantly burned. So that's why you take all your jewelry off. OSHA says you're allowed to wear it if you make it non-conductive, but that's old school 1980s talking. Now with arc flash and knowing what we know and knowing things in metal heats up, that we don't want to have any metal rimmed glasses and anything like that. So even though there's an exemption and an allowance for wearing rings and watches and all that stuff, if you make them non-conductive, don't do it. Just make sure that you protect yourself from arc flash events as well. Okay, tester failure. So this was a tester. This is what it looked like on the right is a phase sequence indicator, and that phase sequence indicator way on the left is showing the same thing on the floor after the failure occurred. So I'm going to guess here that it was probably a transient, and this rating, the meter was not category, UL listed category 4 or 3 rated. So that means the transient is like a spike in the system. It could be 3 times greater than the voltage, for example, caused it to fail. And once it failed, the air was ionized and changed into a 3-phase fault. And in the picture in the middle, you can see all the switchgear and the bus work and all that stuff just completely blew apart. So it had to be a fair amount of fault current on there to cause that to happen. And then you may have seen this before. This is available online. It's called Donnie's Story. It's on YouTube. There's a follow-up to this one as well on there, which is a good story to read about. He survives, but it's an interesting story. Okay, lockout tagout. So you can see this particular lockout tagout is in a high dust area. They've got some breakers with some open bus work on the right. They've got a paper clip that they're putting into the breaker. This place was a very scary place, and you see these kinds of things out there. And it's amazing what happens. Well, we've always done it that way. You've probably heard that a million times yourself, but doesn't mean it's going to be the best way to go. This is where you're going to get statistics. Arc flash analysis. So we want to do an analysis if we can. So what NFPA says that arc flash hazard analysis shall determine the flash protection boundary and the personal protective equipment. And it doesn't say you have to do an engineering study or you have to go by our tables in NFPA 70E. It just says you got to do an analysis to determine the arc flash boundary and determine what the protective equipment is. So if you do an arc flash engineering analysis, this is a label that we put together years ago. We color code them and we put put a kind of a large box with 18.14. You see that's the calorie rating, so we can see. And from a distance, we know it's orange, so we're going to have a certain level of clothing on. Down at the bottom, we also put the fed by information on there on the label, so we know where to lock it out. And then we also put the fault current right on the label as well. So and then we get all the PPE listed. So we put a fair amount of information on there and color code them to make it work. Whoops, I think I went back one here. This is the responsibility of the employer. This is a section that a lot of people don't realize. So the employer sometimes will say, well, we're not going to go in the main switchgear or the bus duct or things that have higher arc flash levels that we suspect have higher arc flash levels based on NFPA cables. We're going to hire contractors for that. So they assume that the contractor knows what levels they're going to have. But they don't. How would they? They need to know a lot of information from your system before that can be determined. And that's where the engineering study comes into play. So even if they use the tables, they have to know what the clearing time and the fault current is. And if they're, the clearing time is not just based on time current curves, but it's also based on maintenance of the equipment as well. So it's the responsibility of the employer to provide that information to the contractors and the employees. So that's where the engineering study comes into play. If you do an engineering study, you got labels on it, you just tell the contractor, go by the labels. That's bang, you're done. You've done what you need to do to tell them what the hazard is. If you have not done a study, then you've got to come up with a little more information so that they can know if they can use the tables or not, meaning fault current. So in that scenario where it was 96 calories, the available fault current from that system would be outside the perimeters of the tables, and it wouldn't work. So that's the kind of information that we need to have. Okay, this says that the host employer is responsible for providing the contracted information. That's just what I just talked about. All right, subpart S. So this is the section I was talking about in 1910-335 that says that the employers working in areas where there are electrical hazards shall be provided with and shall use protective equipment that is designed and constructed for the specific parts of the body to be protected and for the work to be performed. As I mentioned, that was written in 1980, so it's very general, but it works fine for all PPE, electrical PPE. 269 requires employers to protect employees and contractors from flames and arcs. And then it just says that the employer shall assess the workplace for flames and arcs, electric arcs, estimate the heat energy from electric arcs. And they say it in the OSHA standards, a reasonable estimate. So that means they don't have to assess every meter socket, every power line, every substation, switch, and every single part of every system. They can do a reasonable assessment, a specific worst case scenario in substations, worst case scenario in pad mount transformers, those kinds of things. And software, so there's a couple different ones. So 1584 based software, there's a lot of different manufacturers. There are software folks that make this. SKM, Easy Power. There's a bunch of different ones out there that use 1584 as a basis for their calculations, for their engineering stuff. Arc Pro is for usually higher voltages. That's used like above 34.5. It can be 34.5 and above. So that it provides, when you get up into 115 and even as high as 880,000, or I think there's a 1.2 million volt line now in Texas. So Arc Pro would be what you would use for that. You can also use it for some DC analysis as well. There's not a lot of really good software for DC analysis at this point. This is an arc flash engineering study. It's really hard to see, but I have a couple of highlighted ones that are over 30 calories. So on the right-hand side is the incident energy. Next to that is your working distance, and then the arc flash boundary. So those three lines would be used. We would pull out the arcing fault current or available voltage fault current, and then we pull out the fed by information and the name of the panel or equipment, and that would be what would go on the label. This is an example of Arc Pro for higher voltage stuff. So OSHA doesn't say 1.2 calories for the boundary. It talks about 2.0. And basically they're saying cotton's not going to flame up at that level. So they call that the arc flash boundary. So that's, I got 2.02. So roughly you're going to be about 6.5 to 6.7 feet for your arc flash boundary in this particular case. So you can tell, but based on these numbers, how close you can get to that particular equipment before you have to start protecting yourself. Decision-making process, this gets into risk assessment. So when I was growing up as an electrician, we always had to assess the hazards. We had to wear natural fiber clothing. There was no arc-rated anything back then. But now it came out in 2009 in the NFPA 70E, and it's been expanding ever since. It's a really good program to determine risk. I like to put a probability severity chart in there just to kind of give you an idea of what to do for a risk assessment. So I always tell folks, hey, before you start going into any panels or anything, force yourselves to plant your feet at the very least. You should do electrical job brief plan. But this is a little bit beyond just doing that. So you're looking at the risk, not just the hazard, but the risk. And you ask yourself, what if? What if I open this door and this thing blows up? How bad is it going to be? Is it going to be minor, moderate, serious, or catastrophic? Okay, so now I know the severity. Let's say it's serious. And now what about the probability? Is it going to be improbable, remote, occasional, probable, or frequent? Well, it depends on a lot of things. How new is it? Has it been maintained properly? What kind of mechanism is it? In one case I worked it was under salt water for a while during Hurricane Sandy. Well, that's going to increase the likelihood of a problem in a big way. So I'd probably be in the red high risk level with something like that. So then you just step up your protection one level, just to give yourself a little extra protection. And if it's too high, then you just have to go with elimination or one of the others above and not rely on PPE. You have to, try to shut it down if you can. I mean, that would be your ideal way of dealing with it. So you want to start off with the elimination and substitution engineering controls. If you can't do one of those 3 or 4, then PPE is your last resort, and you just have to make sure that your PPE can handle the worst case protection level or hazard level. This is a good example. You got 2 identical switchgears, sort of. They're both 1600 amp switchgears, but one is 1964 and one is 2004. So there may be a big difference in the maintenance on it. There may be a much greater fault current available on the left because it's going to be an older transformer feeding it more than likely. So there's a whole lot of difference between one to the other, even though they're the same size switchgear feeding the same type of equipment. So that's what we have to think about. Mitigating the hazard, there's a few different ways to mitigate it. You can apply distance by remote racking, remote switching. This is like a homemade chicken switch on the left, and he's got a string that he's holding way over there, operating the switch from real far away. You may be able to get a lot of distance between you and the arc flash by increasing the mechanism that you use. Sometimes there's a maintenance switch, and it switches over to the breaker to make it a very fast-acting breaker. Remember that the incident energy of an arc flash is directly proportional to the clearing time. So if you lower the clearing time on a breaker, you're going to lower the arc flash level. There's an arc flash relay that you see in the picture, and that's fiber optics. And this is good because it ties into the trip setting of the breaker, but it only is looking at the light from the arc flash. So it's not changing the breaker to be faster. And that would mess up your coordination for the duration of like a switch, a maintenance switch would do. But it doesn't mess up the coordination because it's just going to go with the switching mechanism that it has and looking at the light hazard. So it works really well. A lot of different remote racking, remote switching devices. This is a CBS ArcSafe. This just gives you one example. So de-energizing, and so again, so you're testing and working and doing whatever you need to do with a hot stick. That's one way of mitigating. And on the left, it's there's a shock hazard with 480 volts and 950 volt DC and all kinds of stuff in this inverter cabinet. And so that's just covering it up to minimize your risks to be able to go into the control cabinet above. So there's a lot of different ways you can do safe work practices. So just determining the PPE, if you have an engineering study done, then you'll go with the labels, and if you don't have one done, you'll go with the tables, and you'll just have to make sure that the parameters of the tables work. But these are the color codes. So I've got 1.2. The picture on the left of the blue label shows a person without a shield. That's under 1.2, and the one to the right is just over 1.2 for the shield. Once you get to 4, then you're going to go into the yellow one, and that would be requiring a balaclava hood once you're over 4 calories. And then once you get up over the other one, you can layer up if you want to versus using a suit. When you're 16.6, you're able to probably wear arc-rated shirt and pants and also coveralls and be up over the 16.6. It's just having a balaclava hood and a shield would be the problem to get that up to 16.6. So you're probably still going to need a hood anyways. Okay. Some other PPE considerations. So you're going to have a hood. If you're going to use a hood, I use a hood all the time. I don't use a balaclava with a shield. I just use a hood all the time, like this. In the picture, it's got air supply, so it keeps me cool, keeps oxygen going. I have a light in the front so I can see properly and well. You do want to inspect it before each use, just to make sure there's no bugs in there, because I did get one in there one day, crawled across my shield, and I brushed it out of the way, but it wasn't on the outside, it was on the inside. So I had to button up what I was doing and quickly get out of it. So it's a good idea to inspect it beforehand. As I mentioned, rubber gloves with leather protectors are ARC-rated now, so they give you ARC-rated protection per NFPA 70E. And then there's just a bunch of other things: earplugs, leather boots, hot stick and high voltage tester and grounds for medium voltage. That would be over 600 volt stuff. Layering charts. This is one from Tyndale, but Bulwark and all the manufacturers will have a layering chart, so you can add them up. And if you add up the value to them, usually it's going to be close to double the rating actually of the system as a tested system is going to be much higher. So I can put on my 10.9 calories shirt and 12.4 calorie coveralls, and I'm at 40.7, even though they only add up to 23.3. And that's me in the picture with my coveralls and my getup. That is an FR rated vest, so it's fire resistant. It's not arc rated, but it won't flame up. It's not going to offer me protection. It's just not going to flame up. But that was a requirement for the DOT that I was working for at the time. A couple of liability cases. So here's a case: the business had to pay $32 million in damages, lack of breaker maintenance, and that's where the arc blast happened because maintenance wasn't done, and so the company had to pay $32 million for that. And here's another case. This is $13.9 million, and it's a result as a failure to perform routine maintenance. So that's basically what you see in the red underlined section on the right. So that, again, that caused an arc flash incident. So that kind of gives you an idea of some of the things out there that are, there's a lot of money involved. You can do a lot of arc flash studies for $13.9 million. And so people think, well, it's just kind of expensive. You look at cost benefit and so forth, but it's a lot more expensive not to. All right, so we're going to come down and break down what we looked at today, and then we're going to take some time for some questions. So first off, we hopefully define what an arc flash is. It's incident energy, and it's measured in calories per square centimeter. That's a measure of the heat and energy from this thing and pressure. And then what causes it? We went through a whole bunch of different scenarios of what can cause an arc flash event, and it's really what we do with the equipment, or if equipment fails and it goes from ground. It usually starts off with a face to ground fault, and then it travels to face. Usually that's how it starts. And when you're talking about the main switchgear and stuff, you have a very good likelihood of, especially on the main side of the main disconnect. So it's on utility transformer side of the main disconnect, you have very long arc flash because you don't have any protection between you and the transformer, and it's going to take a long time to clear that fault, and that's why there's so much damage at that point. So OSHA, we talked about, so in 269, the utility standard, there's a little bit of arc flash data in there, but quite a bit actually, but it only is related to utilities and utility-like work, so it's more like medium voltage stuff. In the subpart S, they have not yet updated that to match up with the most recent NFPA 70E. I expect that's going to come down the pike in another, probably within 5 years or something, I'm hoping, but we'll see how that goes. But they can still refer to NFPA, and it's just the right thing to do. It's a standard, it's a known standard, it's the right thing to do, and just because it's not an OSHA regulation per se, doesn't mean it's not regulatory, or doesn't mean it's not enforceable. And a lot of your states will enforce NEC, and NEC is NFPA 70, so it may be even enforceable as an arm of that. And then talk about the advantages of engineering studies. It gives you a lot more detail and provides a label, tells you what it is, and it gives you information. The problem with the tables, they can give you information, but people don't tend to do an assessment to determine what their fault current and clearing time is so that they know they can use those tables. And that doesn't seem to happen out there, so that's an issue. You want to recognize methods of mitigation, and so there's a lot of different ways to bring it down. And usually if you have another good benefit of doing an engineering study is the engineer will tell you what you need to do to make it less than what you have. And that's usually in the report, and so you know what you need to do. And then, so we talked about the liabilities and some damage, just a couple of them. I've got a whole list of those kinds of things that happen. Okay, so I'm up for some questions. If anybody has any questions, if something comes up later, there's my number and my email address, so you can use that for if something comes up later on.
Wonderful. Thank you so much, Lee. Fantastic content. That was such a great presentation. So before we go into questions, I just want to say thank you all for attending today's event. And Lee, thank you so much for spending the afternoon with us. We have plenty of time for some questions, so if anyone has any, feel free to go ahead and submit them by using that Q&A widget at the bottom of your screen. And Lee, let's get started here. First question, do you mind discussing qualified versus unqualified workers?
Yeah, that's a good question. So qualified worker is one who has demonstrated understanding of construction and operation of equipment, and also understands the hazards related to it. An unqualified person doesn't. So the thing is that people need to know is that qualified electrical workers are different. Every place you go, a generator guy versus a widget maker that is on an assembly line versus a lineman versus a doctor of physics that is doing 1.5 million volt testing. Everybody is considered a qualified electrical worker when they have exposures, and they have to understand what it is they're working on. And so it's got to be specific to them. And that's one thing that you got to think about is the training should be customized and specific to the electrical worker that's being exposed. So, but a non-qualified worker would not typically have or not need to have the knowledge that a qualified would have to have.
Great, thank you so much. And I am seeing a couple questions here regarding a link to the presentation. So today's program has been recorded, and you will receive a link in about 24 hours from the EHS Daily Advisor that will contain a link to the recording. So if you wish to preview it again, you certainly can once we send that over to you. All right, Lee, next question here. What is the most updated method for compliance?
NFPA 70E. So the 2018 is the most recent. 2021 will be out probably around September, October timeframe. So that will be the most updated. I don't think there's going to be too much new that will require electrical safety programs to be updated, your written programs. So that's a good thing. In 2015 and 2018, there were a lot of changes, so we had to do a lot of updates to the written electrical safety programs out there. So that probably won't need to be done, but that would be the closest thing. From a maintenance standpoint, a great guide is NFPA 70B, as in boy. And that's got a lot of good information on how to do maintenance and checklists for all kinds of different kinds of equipment, and it gives you really good guidance on starting up your maintenance program or beefing up your maintenance program.
Wonderful, thank you. And what training options are available to train a workforce that does not have access to any computers?
Well, now, I mean, I've been doing a lot of webinars, and that can be a problem because people that don't have computers can't really attend a webinar class. Some companies that I work with, what they'll do is they'll project it, a webinar, they'll project it through the projector onto the screen. They set up the computer, the laptop toward the front so I can actually see the people. They place the people out there with a social distancing in mind, and I can see them and they can see me for demonstrations and things like that. So it's okay. It's not like being there with hands-on equipment, but it works okay. You know, I mean, it provides the information that you need to have, and there's some interaction because it is live and it's customized, so it usually works fine.
Great, thanks, Lee. I know we're getting close to the top of the hour, so we're going to try to squeeze in a couple more questions here. Next question, Lee. Have you ever come across where employees test electrical equipment to determine if they're working properly with 5 volts and 3,750 amps? Is there any arc/hazards associated with this?
That's a good question.
Yeah.
3,000 amps and 5 volts. So I'm just trying to think of what that scenario would look like and what equipment that would come from.
I just pushed the question to the slide area too, Lee, so if you wanted to take a look at it,
Yeah.
That might help you out a little bit.
So OSHA rules say if it's under 50 volts, they don't care. It's not a problem because there's not enough pressure to push the current through your resistance of your body. But if you're talking about 3,750 amps and you are in line with that, if you remove one wire and touch the other, so now the current wants to go through your resistance, I don't know that the 5 volts would be a big problem. I mean, that the 5 volts would not be a big problem. I think that it would be a problem. I'd have to study that one a little bit more and talk to my my engineer guy that is our vice president, and he would provide a little more detail on that. It's a good question. But can I get back to you on that, Michelle, and you can send it out?
Absolutely. So, Bruce, I know you submitted that question. Lee, once you respond back to me, Bruce, I'll be sending you an email with some more details on that. All right, next question here. Can you wear steel-toe shoes, or is the proper PPE composite toe shoes?
Yes, you can wear steel-toe shoes. They make EH-rated boots with steel toes. I wear them all the time. The electrical rating on boots are basically where the rubber hits the road. It's the sole of the boot. So if you're outside in the grass, electrical rated boots don't do anything for you at all. So it's only where you're like inside and you're standing up. So steel toes are not a problem with the electrical rating.
Perfect. Thanks so much. All right, and we're going to close out with this last question here. What is the best method to train a small workforce, so less than 5 employees?
Well, I don't know that there's a best for 5 versus 20. I think that we do an 8-hour class for new people that are just being introduced to NFPA 70. We also offer a 2-day class. And then for refresher, we go with 4-hour classes, and with webinars, we do 2 hours with refresher. So it depends on the kind of training that you have and the type of people that you have. If you're assembly line workers making widgets, a 2-hour class is probably enough. But if you're a lineman, then you need to have maybe 4 days of classes. So it depends on the type of work that you do as to what that level is. But it's a challenge because if you're, I charge by the day. So if you've got 5 people, it's going to be a lot more per person than it would be if you had 30. So that can be prohibitive as far as the expense is concerned. Webinars are a lot cheaper, so that's a good way to go. But I don't know that there's a best answer except for unless you have a qualified person on site that really learns the NFPA standards and they can teach it internally, that may be a good way to do it. But maybe start by getting NFPA manuals and having to read them and know them inside and out. Have a good electrical written program associated with it.
Wonderful. Thank you so much, Lee. Again, that was such a fantastic presentation, and I just want to thank you so much for joining us today. We really appreciate it. And thank you to everyone in the audience for joining us as well. And one final thanks to our webinar sponsors, AVO Training Institute and Tingley Rubber, for making this event possible. All right, as I did mention, today's program has been recorded, so you will receive an email from the EHS Daily Advisor in about 24 hours after this event that will contain a link to the recording. So again, if you wish to preview it again, if you missed anything, or if you want to pass it over to a colleague, you will receive that in your inbox some point tomorrow afternoon. One final note, at the close of the webinar, you will see a quick exit survey. Make each of our events valuable to you. We would appreciate your input. All right, everyone. Again, thank you all so much for joining us, and I hope you're all staying safe and healthy. Thanks so much.
Thank you.